Good evening, students. In today's session, I will be discussing about the optical isomerism. So, first of all, you should know about optical activity. Take down what is optical activity. Optical activity. See, normal light, when it travels from one place to another place, it goes, let me assume it goes in this direction. And we will take the cross section like this, and they will be vibrating in all directions like this. Okay. So they will be vibrating in all these directions. When it is passed through a prism called a Nicol prism, Nicol prism, when it is passed through Nicol prism, what happens is the vibration, a particular set of vibration will be split, and such type of lights are called plane polarized light. So let me select only two vibrations for our convenience, horizontal and vertical. So the horizontal vibrations are split like this, and vertical vibrations will go like this. And such type of light are called optically active light. Okay, and this phenomenon is known as optical activity. Okay, please draw this diagram. So this phenomenon is called the optical activity. Means that is this plane. This phenomenon is known as polarization. That is splitting of the plane polarized light. Okay, so that is called polarization. And this polarized light, when it is subjected to, or when it is passed through a sugar solution, for instance, now they rotate either in the left side or in the right side. Okay, so this vertically plane polarized light, it can be rotated in this way towards right. When it is towards right, it is called dextrorotatory. When it is rotated on the left side, it's called levo rotation. That is, levo means left. Levo. And based on that, the isomers are named. Do you understand? So dextro isomer, levo isomer. That is L isomer and D isomer. Okay, take down. So dextrorotatory, levorotatory. And this dextrorotatory can also be represented as plus. So plus isomer. Then levorotatory can be represented as minus. So minus isomer. And as far as organic compounds are concerned, if any organic compound is found to be optically active, it should satisfy certain conditions. And what are those conditions? Take down. Conditions to exhibit optical activity. First of all, the compound should have asymmetric carbon atom. It means the carbon atom possessing, 4 valencies, and they are attached to different atoms or group of atoms. For instance, let me say A, B, D, E, like that. So they are differently attached. Such type of carbon is notated as asterisk. So when I put asymmetric carbon atom, it should be indicated by C asterisk, C star. Then they should have no mode of symmetry. They should not have any symmetry. No symmetry. And it should form non-superimposable mirror images. Non-superimposable mirror images. So these are the essential conditions. Okay. What do you mean by non-superimposable mirror image? Let me consider. Look me here. For instance, this is 5 and this is 5. What is 5 plus 5? 10. But in chemistry, 5 plus 5, it becomes 5. It means this is superimposable. Non-superimposable means this is the mirror image of this one, this hand. So when I join like this, now they form non-superimposable mirror images. They don't superimpose exactly. So the molecule should have the structure like this. Okay. So this is known as non-superimposable mirror image. Understand? Next. Now let us consider an example here. For instance, let me check whether this compound exhibit optical activity or not. Right? Now listen. CH3 H. This is above the plane of the board. H and OH. So what is the name of this compound? You can type the answer in the chat. What is the name of this compound? IUPAC name, please type. It's very simple. CH3, CH2OH, what is that? Ethanol. Okay. So this is ethanol. Now let us check whether ethanol is optically active. ethanol is optically active or not. So carbon is attached to CH3, okay, OH, okay, H, okay, but you have the same H here. So it is not optically active. Do you understand? Why? Because it does not have asymmetric carbon atom. So no asymmetric carbon atom, because it is attached, two hydrogens are attached to carbon. Asymmetric carbon atom means carbon atom attached to different atoms or group of atoms. Right? Okay, so let me take the another example. Write down. Deuterated ethanol. What is that? Deuterated ethanol. So deuterated ethanol means, now instead of hydrogen I can introduce deuterium here, right? Now tell me whether it is optically active. Deuterium is attached. Now it is optically active. Why? Because there is what? Asymmetric carbon atom here. Why? Because C is attached to H, deuterium, OH, CH3. So different entities. So when carbon atom is attached to different entities, then it is what? The optically active compound. But at the same time, we have to check the mirror image also. Let me check the mirror image. Please draw this. Okay, right. And this is also known as chirality, optical chirality, or we can say chiral carbon atom. Take down. Chiral carbon atom. Now let us check the non-superimposable mirror image of this compound. Let us consider the same C, this is CH3, and this is hydrogen, this is OH, and this is above the plane of the board. That is deuterium. Now this is a deuterated asymmetric, and we have to prove whether it has the non-superimposable mirror image. So let me say this is C, and the mirror image will be, so CH3 will be here, but hydrogen will go here, and the hydroxyl compound will come here, and D will be here. So these two form non-superimposable mirror image. Take down. Non-superimposable mirror images. Okay. So that is why they are what? Optical isomers. So they can exhibit optical isomerism. Do you understand? So this chiral carbon atom can also be called asymmetric carbon atom. What is asymmetric carbon atom? It is a carbon atom attached to different groups or atoms. Okay. That chiral carbon atom can also be called the chiral center, and it is usually represented by asterisk. Now I will draw another structure and tell me whether it has asymmetric carbon atom or not. Okay, take down. Okay, can you write acetic acid? Try this, not acetic acid. CH3 CH OH COH. What is this? This is hydroxycarboxylic acid. Okay, so does it have asymmetric carbon atom? Yes, because C is attached to hydrogen. Is it not? Hydrogen, hydroxyl group, COOH, CH3. All are different. So you can put asymmetric carbon atom. Take down. So this is the hydroxycarboxylic acid. You know something about amino acid, right? We have got nearly 20 amino acids. Which is the first amino acid? NH2, CH2, COOH. What do you call it? Glycine. Take down. Amino acetic acid. And the next one will be CH3, NH2, COOH. What do you call this one? Alanine. Alanine means that is you have this is the IUPAC nomenclature. What do you call this one? Acetic acid or ethanoic acid. So in ethanoic acid, in the second position, amino is joined. So this is called 2-amino ethanoic acid. All by trivial name, alpha amino acetic acid. Okay, take down. Alpha amino acetic acid. Why? Because this is the amino group and this is the alpha carbon atom. So the amino group is attached to the alpha carbon atom. So it's called alpha amino acetic acid. So similarly, this is alpha, is it not? And this is the propionic acid, is it not? CH3 CH So this is the alpha substitution. So it can be called alpha amino propionic acid. This is the common name. And what is the IUPAC name? 2-amino propanoic acid. What is that? 2-amino propanoic acid. Okay, please note down. Right. Let us consider the next one. We have already discussed about I mean in organic chemistry, diols. Okay, so let us consider diol means what? 2-hydroxy dihydroxy derivative. For instance, you have CH2OH, CH2OH. What is this? Glycol, ethylene glycol. Let me take this ethylene glycol and substitute with methyl group like C. Let me replace this one hydrogen by CH3 and CH. This is OH, H. Okay, right? So what do you call this one? This is 1, 2, 3, and you can put CH3. So 1, 2, 3, 4. 4 means butane. So butane and 2, 3. So butane 2, 3 diol. Do you understand? Butane 2, 3 diol. What about this one? This is 1, 2 ethane diol. Okay, 1, 2 ethane diol. This one 1, 2, 3, 4. That is butane 2, 3 diol. So butane 2, 3 diol or 2, 3 butane diol. Are you able to follow? Now let me check the that is the asymmetric behavior. Let us consider this CH3 OH H, and this is a different entity. So this is asymmetric carbon atom. What about this? This H OH CH3, different entity. So this is also asymmetric carbon atom. And we need to check the plane of symmetry. There is no plane of symmetry, and it can easily form the non-superimposable mirror image, so it is optically active. Suppose if this compound is of trans isomer, is it not? Because OH groups are on opposite sides. Suppose if it has the cis isomer like this, for instance, CH3, CH3, H, OH, H. So this is not optically active. That is, they are optically inactive. Not optically active. Why? Because you can find a plane of symmetry here. Is it not? So when you have this cross cut, now this is the mirror image of the upper part. So it is not, so it means what? It forms a superimposable mirror image. I mean, it has the plane of symmetry here. So that is why it is not optically active. Okay, not optically active, no doubt. Because of plane of symmetry. Write down, because of plane of symmetry. Okay. Next one. Shall I proceed? Noted down. Okay. Let us consider tartaric acid. Tartaric acid. What is tartaric acid? It is available in tamarind. Let us consider. See, this is tartaric acid. It can be simply represented like this. This is a simple way of writing. COOH. It's a dicarboxylic acid and hydroxy dicarboxylic acid. HOH, and this is OH, and this is H. Right? So this is tartaric acid. So if you want, you can expand COOH, CHOH, CHOH. This is COOH. So this is optically active. Why? Because it has a asymmetric carbon atom here. So it is optically active and there is no plane of symmetry and it can form non-superimposable mirror image. So all the three conditions are satisfied. But when you consider meso-tartaric acid or the cis type of tartaric acid, COOH, this is a trans isomer. This is not optically active. Do you know why? Because there is a plane of symmetry. Okay, there is a plane of symmetry. So when a molecule exhibits any type of symmetry, then definitely it cannot be a what? The optically active compound. Do you understand? If it has that is n number of asymmetric carbon atom, it can have 2 power n number of isomers. Okay, so the number of, take down the number of optical isomers possible or 2 power n. So you can adopt this formula. Based on that you can arrive at. So n means here 2. Why? Because symmetric carbon atom. So n represents number of asymmetric carbon atom or chiral carbon atom. Okay. Now we can talk about the, if it is a D isomer, okay, if it is D isomer and the other one can be L isomer, so that can be called DL pair of tartaric acid. And definitely they will be having a mirror image. So we will draw that one also. Have we finished with this structure? Shall I proceed? Okay. Let us draw the mirror image. COOH, and this is HOH and HOH, and here COOH, then OH and H, similarly H and OH. Do you understand? So they are called D and L pair of tartaric acid. Okay, take down. And the mixture of these two can be called, in fact, when they mixed together, they are resulting optically inactive mixtures. Such type of optically inactive mixture by external compensation, by mixing D form and L form, that is DL form, can be called racemic modification. Okay, so please note down. So the mixture of these two can be called D plus L, result DL, equimolar ratio. So when they are mixed in equimolar ratio, so DL, they will be cancelling out each other their optical rotation, and that is why it's called DL form. And this DL form is optically inactive. Take down. Optically inactive. Okay, how? Because of external compensation, that is by the combination of equimolar ratio of D and L form, and they are also called racemic modification. They are called, also known as racemic modification. Write down racemic modification. But in the case of meso tartaric acid, I think I already explained here. This is the meso tartaric acid. This is meso tartaric acid. This meso tartaric acid, it is not optically active. Why? Because of internal compensation. Do you understand? Because of internal compensation by the plane of isomer. Are you able to follow? That is, there is a plane of symmetry, not isomer, plane of symmetry. Okay, so meso tartaric acid is not optically active. It is because of internal compensation. Okay, by internal compensation. So they are optically inactive by internal compensation. Whereas DL form is by external, optically inactive by external compensation. That is, they mutually cancel out each other's rotation. Do you understand? Please note down. Shall I proceed? Now let us compare the Racemic versus meso form. Take down. Racemic form of tartaric acid versus meso form. Here let me write racemic form, and this is meso. Racemic form, as I already told you, that is, this mixture can be, that is, this can all be represented as DL form. DL mixture can be separated into optically active isomer. Whereas meso it's not a mixer, it is a single compound. Cannot be separated, no question of separation. Then they are optically inactive. They are optically inactive. Why? Due to external compensation. External compensation means what? By mixing equally, that is equimolar mixing of D form and L form. So it's called external compensation. Whereas when you look at meso, it is optically inactive. Why? Due to internal compensation. The molecule of isomers are chiral, whereas here they are not chiral. Okay, take down. So these are the major differences between racemic and meso form of tartaric acid. So this is the regular question asked. The meso form can also be called diastereoisomer. Can make a note of it. Meso form can also be called diastereoisomer or diastereomer. Diastereomer. It means that is, it doesn't have the stereo isomerism property. Diastereoisomer or diastereomer. Okay. And this D and L form, as I already told, can be separated into optically active isomers, D form and L form. and their sign of rotations are different, and they are called enantiomers. So they can be called enantiomers. So what are enantiomers? That is isomers with a different sign of optical rotation can be called enantiomers. Enantiomers generally they have identical in all physical properties, in all properties generally, except the sign of rotation. Okay, take down. So what are enantiomers? Enantiomers are the optical isomers with all properties equal except the sign of rotation, optical rotation. Whereas diastereoisomer, they differ in all physical properties. So since they differ in all properties, they can be easily separated because physically they are distinct. Whereas enantiomers, that will be very difficult to separate unless otherwise it is subjected to optical activity. So these are the salient points to be noted down. Now let us move to notations. Take down. Representation of configurations or the molecule by optical rotation. One method is known as DL system. It is also called a Fisher system. Another is RS notation. Now let us discuss DL system. Shall I proceed? DL system, also known as Fisher system, Fisher notation. Here, let us discuss with an example. Glyceroldehyde. What is the formula of glyceroldehyde? Let us consider glyceroldehyde. That is, you know glycerol. What is glycerol? CH2OH, CHOH, CH2OH. So when the first primary alcohol is subjected to oxidation, then it becomes glyceroldehyde. So CH2OH becomes CHO. So CHO, CHOH, CH2OH. This can be represented like this. That is CHO, here H and OH, and this is CH2OH. And what is the mirror image of this one? So let us draw the mirror image. Okay, so HO, and here comes H, and then you have CH2OH, CHO, right? So this is known as, that is D-glyceroldehyde. Okay, or it can be called plus glyceroldehyde. Similarly, this one is L, that is L or minus or minus glyceraldehyde. This is glycerin or glycerol. Okay, and here the designation is given as D. Take down. This is D. This is L. Write down. So by convention, you have to write down always the oxidized group at the top and unoxidized one, that is reduced part, at the bottom. When you have got CHO and CH2OH, which is the oxidized part, CHO is the oxidized part, that should be given at the top, and at the bottom you have to write down CH2OH. Okay, so you please mention that one. Okay, now as I mentioned, more oxidized group is shown at the top and the reduced group is shown at the bottom. So this is by convention. And you must also note down another important point, that is the chiral carbon atom should be viewed in such a way. Chiral carbon atom, or chiral, you can say chiral molecule, because we are talking about molecules. So chiral molecule should be viewed in such a way hydrogen, then halo group, they lie above the plane of the board, so plane of the paper, and R1, R2 lie below the plane or the paper. Okay, now let me draw. So do you understand this point? Okay, so the more oxidized part, let me write down a sample example. Let me consider C here, H X, and this is oxidized one, this is the reduced one. So this is the way you have to write down. So if it is written like this, then it is D form. And what about the mirror image of this? You can write C. Now at the top R2 and below R1. Now the CX, X and H are interchanged. Laterally by 180 degree it is rotated. So it is the L form. Okay. So you please note down what is the oxidized group. The oxidized group here is R2, is it not? So this is the R2 group. Got it? So that is why I have written at the top. What are the oxidized group? Oxidized groups are usually COOH group, then CHO group, and then keto group. Okay? And reduced groups are, that is this one. Reduced group, that is R1. They are represented by CH3, CH2OH, etc. Okay? And X represents halogen, is it not? Otherwise, an heteroatom also, any atom, not only halogen. So X may represent, that is X. X represents a different atom apart from carbon, hydrogen, oxygen. So you can put heteroatom. It can be anything like chlorine, bromine, iodine, and even hydroxyl group, right? Then NH2 group, amino group, etc. Okay? Have you noted down? You please note down quickly. Let me have my coffee. Any doubt? Right. Now let us look at the projection formula of the same. Take down projection formula. So you have to practice by drawing all these diagrams. So the first one, D form, can be represented like this. So R2 at the top, right? Then R1 at the bottom. At the bottom means above the plane. So not above the plane, below the plane. R1. And here above the plane. This is H. and this one X, right? So this is D form. So here the dotted line indicates below the plane, and that wedge shaped bone indicates above the plane. Okay, so let me draw the mirror image of this. So how we can draw? Put C. Now the wedge shaped hydrogen bond there. Okay, so this is on the right side, and below the plane at the top R2, and X will be here. Okay, so this is L form. Finished? Right. So let me move to the next example, that is DL lactic acid. DL lactic acid. Take down D and L lactic acids. Lactic acid is present in sugar, milk. Lactose, sugar we used to say. So lactic acid. Here CH3 HOH COOH. This is lactic acid, D lactic acid. And what about L lactic acid? We have CH3 COOH HOH. This is the L form. Okay. Next, let us check whether the tartaric acid has which type of notation. Tartaric acid. So generally it is based on the second carbon atom from the bottom. So you know tartaric acid, COOH, then HOH, OH, H, and then COOH. Okay, so this is equivalent. Now the entire set can be written as R simply. Okay, this can be represented as R. It is not alkyl group, but for our convenience we can write down. So R COOH, and this is OH, this is H, right? And now listen. So what is our convention? The COOH part should be written at the top, is it not? So let us check. The oxidized part should be written here. Okay, so automatically R will come down. Now you can write H and OH. As I already told you, OH, that is the heteroatoms, should be written on the right side. Okay. So when the heteroatom is on the right side, then it represents D configuration. Do you understand now? So this is D configuration. இதெல்லாம் வந்து கார்போஹைட்ரேட் பயோமாலிகுல்ஸ் எல்லாம் ரொம்ப யூஸ்ஃபுல்லாக இருக்கும். நெக்ஸ்ட், இப்போ எல் கான்ஃபிகரேஷன் போட முடியுமா? வெரி சிம்பிள். என்ன பண்ணுவோம், இந்த OH தூக்கி லெஃப்டில் போட்ட வேண்டியது, அவ்வளோதான். ஸோ கேன் யூ ட்ரா த எல் கான்ஃபிகரேஷன், that is L-tartaric acid, completely like this with these three structures? Okay, so please draw and send me the photo in Telegram. Take the snapshot, let me check. Do it fast, quickly. So I want L-tartaric acid with the same representation. You should represent by these three figures. Okay, now please check your result. Let me write. So you had to keep the OH on the left side. That is, take this, so here comes the OH. Okay. Now you have to consider this part as R. The same strategy, and the OH is on the right side. Now you can rotate H, OH, OH, H. Now it is declared as L form. Right? I hope now you should be able to understand the difference between this D configuration and L configuration. Right? So in the next class, I'll be discussing about RS notation. So if you've got any doubt in the concepts so far we have discussed, you can ask me. Otherwise, let us leave the meeting. Any doubts? So let us wind up this session and we'll continue at 9 p.m. after the dinner. Okay, for +2 session, and we need to continue the organic chemistry, the remaining part in the phenols and alcohols and phenols. Right? So thank you very much for watching this video.